we have been discussing the motion, fluid flow in the straight lines, the streamline, and so on. But also, whenever in a real fluid there is viscosity, there is invariably vorticity and rotationability. So that we have also go through and define. And as we know that the vorticity vector zeta is given by curl of V. So curl of V is a vector. It will have a direction, and V here is velocity, and its whole equation in the component form has already been given to you. Another term that we use in this one is rate of rotation. One is the rotation that is introduced, and therefore the term vorticity. So wherever there is viscosity playing a role, wherever the fluid is flowing, we will have vorticity there. And then the terms that we use to measure these things, another thing is rate of rotation. If it is rotating, with how much rate? How do we calculate it? And how do we represent it? So that we denote by rate of rotation normally is denoted by omega, the Greek alphabet, although it looks like W, but it's here, this is supposed to be omega, and omega is equal to half of curl of V. That is half of zeta. Again, that is an Greek alphabet. So half of vorticity. So del cross V multiplied by half will represent the rate of rotation vector. So if we have to see, so this is rate of rotation is half of vorticity. But if we have to say how much is vorticity, vorticity is then twice of angular velocity or rate of rotation, or twice of omega. So 2 omega is equal to vorticity vector. Whenever there is a vector, and particularly the cross product occurs, then you know that all vector quantities have direction. Scalar quantities, they don't have direction associated with them. They are just measurement units. But when it comes to the vector, then there is always a direction associated and a force is being applied, and we want to know if it is motion, acceleration, velocity vector, or whatever, or in this case, in this context, the vorticity vector, then in which direction it's moving. Then the right hand thumb rule is used, as you can see in the picture, that if you can see it, if there is a vector A, and these are mutually perpendicular lines, as we take in rectangular coordinates x, y, z. So this is in the x direction. If it is so, this is, let us say, the y direction. And if we are trying to rotate the motion, then the resultant vector, the vector will be moving in the thumb direction, in which the thumb is showing its direction, and that is the right hand thumb rule, which we used to study when we were studying vector quantities or vector calculus. If we want to see, let us say, in another plane in three-dimensional motion, if I want to show you that how does it reflect, then let us say that these two are perpendicular lines. X, this is x direction. Let us say this is y direction. And there is a vector u in this direction. There is a vector v or a or b in this notation. A is in the x direction, and the vector b is acting in the b direction, y direction. And if we are trying to rotate it, then what will be the direction of the resultant vector? And you will see, according to the right hand thumb rule, or even to the with the right hand, you try to move the screw. If we try to move a screw in the anti-clockwise direction, then it is moving inwards, and if we are trying to move it in the anti-clockwise, the anti-clockwise direction is taken to be as the positive direction. If it is, we are trying to rotate it in such a way that the x direction is moving into the y direction, so the rotation is going like this. And if we try to do that, then you will see the screw will be moving upwards, as we see this plane, and that we take as x, y, z. This will be representing z direction if we are talking about a rectangular motion which are perpendicular mutually. So the resultant vector will be moving in the z direction, and this is the way to calculate it. And it's very important that we need to know which way the vector will be moving, or the resultant force will be acting. If vorticity at a point in a flow field is non-zero, if vorticity is non-zero, so obviously that means that a rotation is taking place there. So there is rotation, and therefore zeta is non-zero. We call it the fluid flow is rotational. And if zeta is 0, then the fluid flow is irrotational. That is, there is no rotation there. And this type of things can happen in many variations. One of them, that there is the fluid is inviscid and there is no viscosity, and therefore that can happen. But there can be other examples also, which I will be mentioning soon. Physically, the fluid particles in a rotational region of flow rotate end over end as they move along in the fluid field or flow field. The difference between rotational and irrotational is that you can see the fluid moving, and as if viscosity effect is reducing at a certain distance, then the fluid is becoming irrotational at a distance, at infinity, or at a larger distance away from the place where viscosity is playing its role. It's non-zero and cannot be ignored, but where it is zero, or if its effects are negligible as compared to the terms that are represented by velocity field or velocity field components or other terms that are occurring in the motion, we consider that part of the fluid flow as irrotational. You can see here, if we imagine that a fluid field, that a flow is moving from left to right, as you can see, and there is let us say a solid body over which the fluid is moving here in this picture from left to right. Close to the boundary, because of the viscosity, the fluid tends to stick to the wall or to the solid boundary, whichever it is. So the velocity along this line will tend to be zero. But as it moves away from here, you can see the velocity is slowly increasing. So at this point it is zero, that is along this line, and that is because of the viscosity. But as it moves up, it's slowly increasing, and you can see this path. And away from this solid boundary, away from this, there is a region where the fluid is behaving as if there is no viscous effect taking place at all. And the viscous effect is very visible in this area. And this is also being tried to show in this picture. If you see this picture, then you can see the rotation being introduced, and the rotation, you can see that the particles that are being represented, although it's being shown as very big, small particles will not be that big, but this is just to show you how it affects. And so you can see if there is no rotation here, but as due to viscosity, there is a small rotation introduced, so slowly it has rotated, it has moved, and it continues to rotate. As you go away, you can see the particle is significantly rotating. But away from it, where there is no viscosity, you can see that the particles stay in their shape. They retain their shape. And therefore, this area is almost irrotational. And we call it as outer area away from the solid body. And the velocity profile here becomes almost uniform, but close to a solid boundary if there is a fluid flow taking place, and due to viscosity, it sticks to the wall. The velocity there is zero. As it slowly moves away from this, we observe that the fluid field is slowly increasing. And there is a region. There is a region in which, and this region is reflected by the gray area, and this region is called as boundary layer. So within the boundary layer, viscosity is showing its effect, and the rotation is also taking place. But as it moves sufficiently away, it becomes non-rotational or irrotational.